Hello and welcome back to the course of Fundamental of Electronics and Electrical Engineering. The topic that I am going to discuss in this video lecture is generation of three-phase alternating EMF, three-phase voltage. In the previous video lecture of AC circuits, I have already discussed about the single-phase AC circuit, analysis of single-phase AC circuit. In this video lecture and upcoming video lecture, I am going to discuss three-phase circuits and analysis of three-phase circuit. So let us start the generation of three-phase EMF. But before that, why three-phase system is required? Which are the advantages of three-phase system? So single-phase system we have studied, or single-phase circuits we have studied. Single-phase generation have limited application. There are certain application in which single-phase supply cannot work. So we require a polyphase system. Poly means what? Many. So as the number of phases are increases, advantages of the generation, advantages of the system also increases, but advantages are not proportional with the number of phases. But out of many polyphase systems, three-phase system is found to be economical. That's why three-phase system is widely used. Now, which are the advantages of three-phase system? So first one, electric power is always generated and distributed in three-phase because it is having its own advantages over the single-phase system. Suppose taking the example of one single-phase and three-phase system, both are having same size, then output of the three-phase machine will be higher than single-phase machine. So for the given size and voltage rating, same voltage rating, three-phase alternating require less space and the cost of the system also reduces as compared to the single-phase machine or single-phase system. As far as transmission and distribution is concerned, three-phase system requires less copper or conducting material than the single-phase system, because if this three-phase system is there, higher amount of power can be transmitted. So cross-sectional area of the conductor also reduces as compared to the single-phase system, single-phase generation. It is possible to produce the rotating magnetic field in the case of three-phase system, which cannot be done using single-phase system. So rotating magnetic field can be generated with the stationary coils using three-phase system, and because of the rotating magnetic field, three-phase motors are self-starting. Single-phase motors are not self-starting, that I am going to discuss in the upcoming video lecture of electric machine. So this is the advantage of three-phase system. Motor is nothing but the system, machine. So three-phase system, three-phase motors are self-starting. Next one, three-phase system gives a steady output. As far as the single-phase system is concerned, it does not give steady output. Three-phase system always gives the steady output. Single-phase can be obtained three-phase. This is also advantage. If we generate the three-phase system, we can also obtain the single-phase from the three-phase. The power never falls to zero. As far as the single-phase generation is concerned, power may fall zero many times, but here power will never fall to zero. Power factor of the single-phase motor is poorer than the three-phase motor for the same rating. So for three-phase system, power factor is improved as compared to the single-phase system, and efficiency of the three-phase systems is also high. So these are the advantages of three-phase system over the single-phase systems. That's why power is always generated in three-phase form, not in single-phase form. Now moving towards the generation of three-phase EMF, and we know the principle behind the generation of alternating EMF is nothing but the Faraday's law. So according to the Faraday's law, if conductor cuts lines of magnetic flux, the voltage is induced in the conductor or coil. So if there is a stationary magnetic field, and if we rotate the conductor, the EMF will induce in the coil. So, and direction and the speeds are also important whenever EMF is generated. Now the requirement to generate the electric current or EMF is, first we required a strong magnetic field, then conductors are also required, and relative motion between conductor and magnetic field. That is important. If both are stationary with respect to each other, then no EMF gets induced, because if magnetic field and conductor is stationary, so magnetic line of force will be not cut, and so EMF will not be induced. So there is a relative motion between there is a must requirement that then there should be a relative motion between magnetic field and conductor. So here you can say there are the two magnets, and magnetic fields are generated because of that, and three coils are rotating in that magnetic field. Now as we have to generate the three-phase voltage, three-phase EMF, number of coil required will be 3. In the case of single-phase generation, only one coil is required. Here winding is divided into the 3 groups. and all groups will be isolated, will be displaced by each other by 120-degree electric angle. So here you can see three coils which are displaced by 120-degree are placed in a magnetic field which are rotating by some prime mover, and according to the Faraday's law of electromagnetic induction, current voltage is induced in that, and that voltage, and because of the voltage, current will start to flow, and that alternating voltage current will flow through brush to the load. So this is a basic arrangement, basic setup for generation of three-phase EMF. So as I told you here, in the three-phase AC generator, three coils are required, and coils are displaced by 120-degree each other. The coils are fastened rigidly together. All the coils are made to rotate about a fixed axis in the uniform magnetic field. Here you can see the basic setup. N and S are the poles of electromagnetic. These are the electromagnetic line of force. Magnetic line of force. In that, three coils R1, R2, Y1, Y2, B1, B2 are placed, which are connected to same shaft. So all will be rotated simultaneously. Coils are made to rotate in anti-clockwise direction, and you can see the angle between R1, R2 and Y1, Y2 is 120-degree. Angle between R1, R2 and B1, B2 is 240-degree. Angle between Y1, Y2 and B1, B2 is 120-degree also. Now, the ends of each coils are brought out. All the coils are connected together, and three ends are brought out through the slip rings and brush arrangement to collect the induced EMF. So the EMF generated will be brought out by means of slip rings and brushes. Here ERY, suppose ER, EY and EB are the induced EMF in the coil R1, R2, Y1, Y2 and B1, B2 respectively. All the voltage and EMFs are having same magnitude and same frequency, and as all the coils are displaced by same angle, all the coils are rotating in uniform magnetic coils, all the coils are rotating with uniform speed. So all the EMFs have same magnitude and same frequency, but all the coils, EMF induced in all the coils will not reach maximum value simultaneously because all the coils are displaced 120-degree from each other. Now suppose in this particular position, ER is assumed, R1, R2 is assumed to be a reference coil. So ER is assumed to be reference and is 0 in this particular situation, in this particular position for the instant shown in figure, because here flux induced will be maximum, but EMF induced will be 0. Now at that instant, EY will be displaced 120-degree from ER, and similarly EB will be displaced 120-degree from EY. So EB will attain its maximum value after 240-degree ER. It attains its maximum value 240-degree after ER. EY will attain its maximum value 120-degree after ER. So when R1, R2 gets rotated 90-degree, then maximum flux, maximum EMF gets induced. Now at this instant, EY will be displaced by 120-degree from ER. Similarly, EB will be displaced by 120-degree from EY, and EB will attain its maximum value 240-degree after EY. So here you can see all the coils are rotating in anti-clockwise direction, and according to that EMFs are induced in each coil. So these are the voltage waveform of EMF. ER, this is a yellow color waveform, is a waveform of ER which is assumed to be a reference one, and according to the motion of the coils, EMF gets induced in the coil. If we plot the graph of EMF, then we will be attaining this kind of sinusoidal waveform. Now here you can see EY will attain its maximum value after 120-degree of ER, and EB will attain, this is a green color waveform, is a waveform of EB which attains its maximum value after 240-degree of ER. Now EMF induced in these coils can be represented by mathematical equation, that is ER1 R2 is equal to E0 sin omega t, because it is assumed to be a reference. There is a no phase shift, so angle is 0, phase angle is 0. Now E1 Y1 Y2, that is a EMF induced in Y1 Y2 coil, it is given by E0 sin 2 pi by 30 sin omega t minus 2 pi by 30, that is nothing but the 120-degree. So both is having same frequency and same magnitude, but EY Y1 Y2 will attain its maximum value to 120-degree after ER1 R2, and similarly EB1 B2 is equal to E0 sin omega t minus 4 pi by 3. So here you can see EB1 B2 attains its maximum value 240-degree after ER1 R2, or it attains its maximum value 120-degree after EY1 Y2. Now these these are the mathematical expression of induced EMF in the coils, which can be here E0 is a peak value of the induced EMF and omega is a angular velocity of the coil and as a T is a time instant. Now this can be represented in waveform also. So here you can see it is a graph of voltage versus time. ER1R2 is a reference. ER1R2 is a EMF induced in the reference coil, that is R1R2. So it will be starting from 0 degree. So it completes its one cycle in 2 pi radian, that is a 360 degree. Now EY1 Y2 will be starting from 120 degree and it attains its maximum value 120 after EY1 Y2. ER1 R2 it attains its maximum value 90 degree. In EY1 Y2 attains its maximum value at 210. So EY1 Y2 attains its maximum value 120 degree after ER1 R2. And if we extend this waveform over here, so we'll be getting this kind of waveform. Now third one is VEB1 B2. So EB1 B2 will be starting from 240 degree. So it will be starting from 240 degree. Here we can see. So angle between ER1 R1 R2 and EB1 B2 is 240 degree. Now here we can say it attains its maximum value at 330 degree. So it attains its maximum value 240 degree after ER1 R2. And if we extend this waveform, so we will be getting this kind of waveform for EB1 B2. Or we can also say that EB1 B2 is leading ER1 R2 by 120 degree. It is lagging behind ER1 R2 by 240 degree, but it leads R1 R2 by 120 degree. So this is how you can draw the waveform of alternating three-phase EMF. All are having same magnitude, same frequency, but all are displaced by 120 degree from each other. Now, to identify the phases, color code is given. So three phases are given the color code, that is red, yellow and blue, to identify individual phases. With red phase is assumed to be a reference phase. The normal sequence of rotation for three-phase supply is red followed by yellow followed by blue, that is RYB. Now if red phase voltage VR1 R2 is taken as a reference voltage, as we discussed earlier, then phase sequence will be RYB. Now what is phase sequence? That I am going to discuss. So the voltage in the yellow lags VR1 R2 by 120 degree, as I told you, and voltage in blue phase lags VY1 Y2 by 120 degree. Or we can also say that voltage in blue phase leads red phase voltage by 120 degree. So based on this discussion, we can define the phase sequence as a sequence in which voltage in three phase reach their maximum positive values. So here we already seen that R phase attains its maximum value first, then Y, then B. So phase sequence is RYB. So we can define phase sequence as a sequence in which phase attains its maximum value. In India, generally RYB phase sequence is preferred. Now moving towards the phasor diagram from three-phase alternating EMF. So R1 R2 is taken as a reference. Then Y1 Y2 lags behind the R1 I2 by 120 degree and B1 B2 lags behind R1 R2 by 240 degree. Or here we can see the angle between all the phases are 120 degree. So here we always assume that phasors are rotating in anti-clockwise direction. So here we can say B1 B2 is lagging behind R1 R2 by 240 degree, or B1 B2 leads the R1 R2 by 120 degree. So this is how we can draw the phasor diagram for three-phase EMF. So this is all about the today's video lecture. In this video lecture, I have discussed about advantages of three-phase system over single-phase system, basic setup for generation of three-phase alternating EMF, then finally draw the phasor diagram for three-phase EMF. Hope you enjoyed the video. See you soon in the next video of the AC circuit. Thank you for watching.